All right, so continuing with our overlapping and disjointed probability. Um, so the first thing we're going to talk about today is um, finding probability of A and B. So yesterday was A or B, like we did the card examples, a 10 or a face card. So that means if I pull it out, if as long as it's a 10 or it's a face card, I'm good. Or it was, the other one was a face card or a spade. So as long as it's either one of those. Okay, so today it would be like, we're going to do a different kind of example, but it would be like a face card and a spade. So it's kind of more limited in like scope because it eliminates all the face cards that aren't spades, and it eliminates all the spades that aren't face cards. So there's only like those three versus it was like 22 or something that like fit the or category. So we have a formula that we use, and I'm going to adapt it slightly from what you would see in the book. Um, so the way that they write it, well, they just write like a P. So if it's probability A and B is going to equal the probability of A plus the probability of B minus the probability of A or B. So you kind of have to figure out all of them to actually get the actual answer. So the situation, and this is example 3 in the book, but we have 200 students. And of those, 113 are varsity athletes or on honor roll. There are 74 athletes, and there are 51 on honor roll. What is the probability that a randomly selected senior is both a varsity athlete and on honor roll? Okay, so probability of A, let's call like A the athletes and B the honor roll, just because that's the way they were listed in the problem. So, we would just plug in our information into the formula. So the probability of A is 74 out of 200 students. Okay, and then probability of B is 51 for the honor roll out of 200 students. And then we're going to subtract the A or B. So remember, when we do A or B, we add them together kind of thing, but we have 113. It's given to us. Okay, and so, because remember, like, you don't just add 74 and 51 because it's not 71 that are just athletes and 51 that are just honor roll, and none of them overlap. There are some that overlap, which is this or part. So then I just do 74 plus 51 minus 113, and we get 12 out of 200. Okay, or 0.06 or 6%. So you have a 6% chance that of randomly choosing a student that is both a varsity athlete and on honor roll. So the or numbers are always going to be higher because I win, so to speak, if I get this one or this one. Where if you have to have both, it's always going to be a significantly smaller number. Okay? So here, when you do and, we have this formula that we need to like look at. Okay, so there's kind of a formula like the other ones where it was like the or one, you did A plus B, and then if there were some that overlap, you subtracted the ones that were overlapping. So the or one is kind of the subtracting the overlapping kind of deal. Okay, so it looks different, but it is similar to the overlapping event that we did yesterday. So another type of scenario, and this one is can be a little bit convoluted, but it's example 4 in the book. But it says like that it's estimated that 8.3% of Americans have diabetes. And so a lab creates a test, a diagnostic test, that is 98% accurate if someone has diabetes, and 95% accurate if they don't. Okay, so if you're given a test and you have diabetes, it's going to be 98% of the time it's going to be an accurate diagnosis. And if you don't have it and they give you this diagnosis, 95% of the time the test will be correct. So there is some error, obviously. So the question is, if a random person is selected, what is the probability of a correct diagnosis? Okay, so we kind of have like two situations here though. So, if we start off with like everybody in the United States, it's a terrible S, it tells us that 8.3% have diabetes. So therefore, 91.7 don't. It's just they got to add up to 100%, right? So if 8.3% have it, then 91.7% don't have it. And then it said, well, we have this like test that is 98% accurate for people that have it. That means it's 2%. So this would be like a correct diagnosis, and this would be an incorrect diagnosis. Okay, and then the people that don't have it, 95% of those is going to be a correct diagnosis, and 5% incorrect. Okay, so, what's the probability of getting a correct diagnosis? So, what I'm really like wanting to look at is these people and these people. What's the probability that I get someone that fits into that category or that category? Okay, so it doesn't matter which one, I'm interested in a correct diagnosis. So I said or, which means I'm going to add those two things together. Okay, but I have two different paths to go on. So a while back we did like what's the probability of this and this. This, like, what's the probability that I roll a 2 and then I flip heads, or whatever. So we would multiply those two probabilities together. What's the probability I roll a 2? 1 out of 6. What's the probability I flip heads? 1 out of 2. And then we would multiply those two things together, 1 out of 12. That's the probability. I multiply the two things together. Okay, so same thing here. I have to find, like, what's the probability that someone has diabetes, and then what's the probability that it's a correct diagnosis? Well, it's 8.3% and 98%. So those are the two probabilities. I'm not going to write them as a fraction to multiply them together, but I can do like as a decimal. Okay, and so when I multiply those two together, 0.083 times 0.98, I get 0.08134. Okay, and then I'm going to do the same thing for the bottom part. I can put 0.917 times 0.95, 0.917 times 0.95, and I get 0.87115. Okay, and then when I add those together, plus 0.08134, I get 0.95249, or we can say like 95.2%. Okay, and so some people look at this and say, well, it's 98% here and it's 95% there, like wouldn't it be like right in the middle? Because they're both like correct. No, because there's a lot more people in this bottom category. 91.7% don't have it, and only 8.3% do have it. So the 91.7, it's pulling way closer to 95 than it is to 98. Now, if it was 50-50, 50% have it and 50% don't, then yeah, it's going to be right in the middle of 98 and 95. But whichever side has more in a situation, it's going to pull a lot closer to that like number. Okay, so if it was 98% accurate for the people that don't and 95% for the people that do, like if they were reversed, then the answer would be much closer to 98 because there's more people, 91.7%, in that bottom category. Okay, so you kind of have to look at, you're going to, I don't know if you'll have to do a branch like this for all of them, but kind of look at the fact that like I have two situations and then I got to do the probability of someone having it and then multiply it by the second probability that it's 98% like correct. Okay, so if it was what's the probability of choosing someone with an incorrect diagnosis, you would do the 0.083 times 0.02 and 0.917 times 0.05. Okay, so it's kind of a different like setup of a problem, but you only have 7 problems to do today, and some of them I think go back to what we did yesterday, where you'll have like disjointed or overlapping events. So it's not all just the stuff that we talked about right now. Okay? All right, that's all I got for you today. Have a good day. We'll talk tomorrow.